Hello and welcome to the section of the chemistry tutor. In this section we're going to begin a discussion of some of the most fundamental concepts in all of chemistry, and that is the concept of an acid. That's what we're going to talk about in this section. Strong acids and weak acids. So everybody watching this has heard of an acid. You have some idea what an acid is. What we're going to do in this section is kind of move away from the general idea of an acid in everyday language and start to put some real definition to what it is, so that we can start to use these ideas in the context of chemical reactions, right? So what you'll find is that reactions involving acids are really common in nature, they're really common in your body, and so they're really important to study. Now, what do you think an acid is, right? Everyday language, we think of an acid as something that, could burn you, right? If you get dropped into a vat of, really hot, boiling, strong acid, then it could disintegrate your body and burn you, right? That's absolutely true. But it turns out that there are weaker acids that you deal with every day. For instance, inside of a lemon, there's an acid inside of a lemon. That's what gives it that taste, right? That citrus taste to it, right? Most citrus fruits actually contain acids. There's different kinds of acids in your body that your body is using all the time. Acids are very, very common, but we need to break it down and understand what they're doing. I'm going to give you a big picture overview of the importance of an acid before we write down a definition. And by the way, you're going to have to kind of trudge through a little bit of this section is more of a definition section, and I hate doing that, but unfortunately, if you don't nail these definitions and really understand what it is, then later on when we do the problems, it gets harder for no reason, because this stuff is not hard. So let's take a few minutes, we'll get some definitions down. Now, acid we talked about a minute ago, we think of that as something that is corrosive, something that can burn you, right? Well, it turns out that the opposite of an acid is something that we're going to talk about in detail in the very next section from this one, and that's called a base. Acids and base are kind of, if you want to think of them as opposites, they're kind of opposites. When an acid and a base comes into contact with one another, they love to react, right? They love to react, and we're going to spend a lot of time in a few sections talking about these acid-base reactions, right? So in this section, we're going to talk about acids, what they are, how they're formed, what defines what an acid is, and also give you examples of what an acid and what common acids are. In the next section, we'll talk about bases and do the same thing. We'll define them, make a listing of common bases, what makes them a base, and so on. And then the following sections after that, we're going to bring acids and bases together and react them and learn how to calculate what's going to happen, basically, because that's a very important part of chemistry. So, we know what an acid is from an everyday language point of view, right? Let's write down a real definition of an acid here, and I'm going to actually write it on the board, but before I do, I'll just tell you, and you can kind of have it percolating as we write it on the board. An acid is a substance which produces hydrogen ions when you put it in an aqueous solution. Typically, when we talk about acids, we're talking about something you can pour, right? It's a liquid. So that's an aqueous solution. So don't forget the last couple of sections, we talked a lot about aqueous solutions. We said if you put a substance in there, like an ionic substance, into water, then it dissociates, it breaks down into ions, right? So we had lots of examples of how you put stuff in there like sodium chloride, and it breaks apart into sodium ions and chlorine ions in the solution. Acids are nothing magical, it's just a substance that when you put it in the water, it dissociates and breaks down, and one of the things that it breaks down into is hydrogen ions. So instead of sodium ions in the last example, and chlorine ions, when you put hydrogen chloride gas into water, it'll break down into hydrogen ions and chlorine ions. And the definition of an acid that I'll write down for you in a minute is a substance, when you put it in aqueous solution, produces hydrogen ions, and that is enough to make it an acid. And that's really the most perfect definition that you can come up with, because that's basically what an acid is. It produces these hydrogen ions. So let me show you what we're talking about here. An acid, so if you're asked on your test, hey, write down the definition of an acid, really this should be the only thing you need to write down. It's a substance that produces hydrogen ions and we write this as H+. You know how we were doing before in the previous sections when we had sodium ions, we'd put Na+ or something. So this is just hydrogen ions, no different, in aqueous solution. All right, this is exactly what we've said verbally, so there's nothing really different here. Now, this is, you know, the definition of an acid. It's a substance, you stick it in water, it breaks down, and one of the things that breaks down into are these hydrogen ions. So when you have a solution, an aqueous solution, with lots of these hydrogen ions floating around in the solution, then you, by definition, you have an acid. And the more concentration, the higher the concentration of these hydrogen ions you have in the solution, the stronger your acid is, right? So if you're going to make, you know, the really strong acid, you know, in the Batman movies, the Joker falls into, right? Then you have to have a solution with a really high concentration of these hydrogen ions. That really is the corrosive part that rips you apart, and it loves to react. And that's really what's going on when you dissolve something in acid. It's a chemical reaction going on there. These free hydrogen ions is really what's pulling off the reaction. So the more of them you have, the stronger your acid is, as far as the strength of it, as far as the ability for it to react violently. All right, now also, this is the definition of an acid, but there are some characteristics of acids that you might need to know. So acids taste sour. Okay, now obviously, you wouldn't put a strong acid in your mouth. That would be pretty stupid. You'd burn your mouth off, right? But when I say acids are sour, I'm talking about things like lemons. I'm talking about things like oranges. They typically have something called citric acid in there. It's an acid. It's a weak acid, but it's an acid, right? And it's something that we have everyday experience with. But that taste that you have there, that's basically you're tasting the acid that's in there, the hydrogen ions and everything that's interacting with your taste buds, and that's the flavor that you have there. So acids in general are going to taste sour. In contrast with bases that we're going to talk about in the next section, they'll generally taste bitter. So it's a difference in taste perception, but that's not really a scientific definition. That's just something that you might want to know. It's kind of nice, something somebody might ask you on a test. The actual definition of what an acid is up in black. This is a characteristic that you might also have. Also, another characteristic people sometimes list for acids, they react with metal and produce, so I'll put and here, produce hydrogen gas. Again, it's more of a characteristic of an acid. Because of the way acids are constructed with all of these hydrogen ions floating around, in general, if you put metal in there like zinc or like magnesium or like sodium or something like that, a really nice strong metal, you drop it in hydrochloric acid, what's going to happen is just going to immediately start to boil, but it's not water vapor coming up, it's hydrogen gas. So if you had a cup of hydrochloric acid, and if you had a pellet of zinc or sodium or something like that, and you dropped it in there, you would immediately see gas bubbles forming. And if you actually had a balloon and you could capture all of that gas, it would be pure hydrogen gas coming out. Hydrogen is flammable, as you know, so this is dangerous to do. But if you were to do that, that's what you would be capturing. And that is a result. We'll talk about the chemistry behind why it happens a little bit later, but basically it's evolving this hydrogen that's in the solution and pulling it out into, instead of hydrogen ions in solution, it's pulling it into hydrogen gas that comes out of solution. So the definition of an acid is what we have in black. It's a substance that produces hydrogen ions, and we have put it in water. Characteristics that you might be asked or might need to know, they're generally sour as opposed to bases that are bitter, and they react with metals to produce hydrogen gas. Now, obviously we know there's different kinds of acids. There's strong acids and there's weak acids, right? And we talked about the difference. When you have a strong acid, you have a higher concentration of these hydrogen ions, so it's going to be more reactive, more corrosive, burn you more if you touch it or something like that. And then you have the weak acids, which are generally, have the weaker concentration of these guys in here. So what I'd like to do is expand a little bit on that and talk a little bit about strong versus weak acids, okay? So let's talk about strong acids first, right? That's what everybody wants to know about anyway, right? What can an acid actually do? So the definition of a strong acid, we already talked about what it is up here in terms of the hydrogen ions, but it's an acid that completely ionizes in water. These aqueous solutions conduct electricity and are strong electrolytes. All right, so here's my attempt at tying all of this stuff into the last section that we did, the last couple of sections. In the last couple of sections, we talked about strong electrolytes, weak electrolytes. We said if you take a substance, you put it in water, and if it dissociates, which means it breaks down into ions, right, then the more that happens, the more fully it breaks down, then the more of a strong electrolyte it is. And then when you have all of those ions in solution, the more ions in solution you have, the easier it is for electric current to actually flow through there. If you have a substance that, like sugar, it dissolves in water, but it doesn't actually break down into ions very much, then what's going to happen is it's going to either be a weak electrolyte or a non-electrolyte at all because it doesn't actually conduct any electricity. So that was sort of the general category of things you put in water. Now we're talking about these things called acids. That's a substance, when you put it in water, it has to break down. It breaks down. Part of it breaks down into these hydrogen ions. That's the definition of the acid. And when you have a substance that breaks down and ionizes completely in water, then they conduct electricity because there's lots of ions in the solution, and so we call them strong electrolytes. So the bottom line is strong acids are strong electrolytes because by definition, in order to be a strong acid, it has to break down completely or almost completely. So a good example of that, a good strong acid that you'll have a lot of discussions about in your class would be hydrochloric acid. It's a common acid. It's actually an stomach acid also. And it's a common acid that you'll use in your chemistry labs and things like that. So the way you make it is you take this hydrogen chloride gas, HCl gas, you put it in water, and when you do this, it immediately starts to dissociate and break down. So you have HCl. The hydrogen ions are floating around in the water, the chlorine ions are floating around the water, and it breaks down completely. So since it's fully dissociated, we call it a strong acid. And because we have all these ions floating around solution, then the solution's able to conduct electricity. So hydrochloric acid solution should conduct electricity, at least some conduction possible through the solution, right? So don't think of acids as this crazy additional category. Really, it's the same stuff that we've talked about in the last couple sections. Put something in water, dissociates, ions are there. The only difference is you have to have hydrogen ions in order for it to be called an acid. But everything else applies. So strong acids are also called strong electrolytes because of what we have written here. So let's take a minute to write something on the board, right? So we've talked about this verbally. If you take HCl as a gas, so you get that in a gas canister or something like this, and you put it in water. So I'm just going to put an arrow, that means you put it inside of a bucket of water or something like that. What's going to happen is this is going to break down, it's going to dissociate. So you have the hydrogen ions here and the chlorine ions here that come together to form this hydrogen chloride gas. So what you're going to get when you put it in water is hydrogen ions, and now I'm going to put AQ to tell you that this is now an aqueous solution, plus chlorine ions, that has a negative charge, and I'm going to put AQ here to tell you this is now an aqueous solution. So this is really the dissociation reaction, so to speak. It's not really a chemical reaction, it's just breaking apart. So we put it there. But notice that it is balanced. 1 mole of hydrochloric acid follows this equation here. We have 1 hydrogen here, 1 hydrogen here, 1 chlorine here, 1 chlorine here. So we don't have to put any numbers anywhere. That's why it's a really nice reaction to start talking about. But you can think about this thing breaking apart. So now we have these hydrogen ions floating around solution. This is what makes it an acid, right? So every acid that we're going to talk about, once you put it in water, you're going to see something like this. You're going to see some hydrogen ions floating around. That's going to be what makes it an acid. right? And then as we talk about the chemical reactions later on, then these hydrogen ions are going to be doing a lot of reacting with other things later on when we put another substance in there. And that's sort of the chemical reactions that we're going to study later on that deals with acids. But for now, this is what happens when we put the raw material into water. All right, so this is balanced. Now there's one very, very, very important thing that I want to point out to you because it depends on your textbook how you're going to see this written. It turns out the way I'm writing this is HCl breaking down into hydrogen ions plus chlorine ions. It's very simple and easy to understand there because you can look here and see that this has H and this has Cl, so it breaks apart just like this, no problems, okay? But and that actually does happen. If I have a tube and I bubble hydrogen chloride gas into water, that's what's going to happen. However, hydrogen ions, like I've written it on the board, this is so important, so listen up. They do not exist exactly like that when they're in a water solution. I mean, this is a good shorthand way of writing down what is actually happening, right? To visualize what's happening. But when you actually bubble the gas in there and it breaks down in the hydrogen ions, it doesn't actually exist in solution as these little H plus things that are floating around. It just doesn't. So what really happens, so I'm going to put a note to you here because it depends on your book as to exactly how it's presented to you. So I'm going to put a note. H plus as an ion does not exist by itself in water. Really is what we call H3O plus, and that is called a hydronium ion. All right, so I'm desperately trying to present this to you so you don't get confused, and I think it's pretty easy to understand. Basically, this is the shorthand way of writing down what happens. The HCl breaks down into hydrogen ions and chlorine ions. However, if you stick a bunch of hydrogen ions in water solution, they don't exist by themselves. They immediately bond with water because you're basically dumping them into a bucket full of H2O, right? But nature doesn't let hydrogen ions just float around by themselves. They immediately get sucked into a water molecule and kind of bond there with the water molecule. So instead of H2O, you have some H3O floating around. Now when you have H3O, it's an ion because a water molecule has sucked in a hydrogen ion. So this H3O has a positive charge. That's why I have a positive there. And it's called a hydronium ion. So in some books, the way you might see this is you might see HCl goes into water and produces H3O positive plus chlorine. And so it ionizes into these hydronium ions. But the short end of it is, the reason some books, and though I choose to write it this way as well, some books also choose to write it this way as well, because it's easier to understand. The HCl breaks down just like this. And it gets the fundamental point across when we start doing the chemical reactions. So you can write it like this and everything is going to come out just fine. The results of the reaction are going to be fine. The chemical equations are going to be fine. Everything's going to be fine. But just know that behind the scenes, this is really usually tied up with these water molecules. They call them hydronium molecules. So or hydronium ions. So if you see in your book hydronium, or what does that mean? How is this different? Then this is all that's going on. So some books refer to it that way. Some books keep it simplified like this for a while, which is what I'm going to do because I think it's a little easier to understand, and so on. So just keep that in mind. All right, so because of this here, right, so because of the fact that sometimes some books call them hydronium ions, some of them call this guy hydrogen ions, right, because it's a little hydrogen ion, but of course we're just telling you that it doesn't actually float around as a singular hydrogen ion in solution. Also notice that what is a hydrogen ion? Right? A hydrogen ion, if you look at the periodic table, how many protons does hydrogen have in its nucleus? If you look, hydrogen is the first element on the periodic table. That means it only has one proton in the nucleus and one electron circling around, right? So if you create a hydrogen ion like this, then really all you have is the proton. You take the one electron away, and so all you have is a proton left. So a hydrogen ion is a proton. That's all it is. So what I'm trying to say is there's three different ways to write the definition of an acid. that you might run across. And I don't think there's really a need to write them down. I'm going to tell you though, okay? There's 3 different definitions. They're all the same, okay? The first one is what I wrote here. It's a substance that produces hydrogen ions in aqueous solution. So you might see that somewhere. That's an acid, all right? You might also see that an acid is a substance that produces protons in solution. Well, that's the same thing because a proton is a hydrogen ion. We just talked about that, right? And the third thing is you might see that an acid is a substance that produces hydronium ions, H3O+, in solution. And because of what I've just explained to you here, that's exactly the same thing as what we're talking about. So no matter what book you have or what professor you have or whatever resources you're using, it might define an acid as a proton donor or a proton producer, a hydronium ion producer, or a hydrogen ion producer. They're all the same thing, all right? They're all the same thing. So when we write something like, when we write our hydrochloric acid, right, there's basically two ways to write hydrochloric acid. So hydrochloric acid. When we're doing our chemical reactions, there's 2 convenient ways to write it. The first way is the way you might think about HCl, aqueous solution. This is something you use a lot when you're writing chemical equations. We know that when we put this in solution, it breaks apart into these hydrogen ions or hydronium ions or whatever you want to talk about, but it breaks apart. But still, when you're doing the chemical reactions, a lot of times it's easier just to write it as HCl in aqueous solution because that's more of a compact way of writing it. But an equivalent way of writing it would be for you to write it as H plus Cl minus. So I guess what I'm trying to say is sometimes when we're talking about chemical reactions, we might write it as HCl in aqueous solution because we're trying to kind of keep everything compact and nice. But if you want to blow it up into all its glory, you could say, well, the HCl really is broken down into these ions, so we can write those down. And we're going to actually use this form later on when we talk about net ionic equations. When you want to break down every ion in solution, you want to show everything, then you would use B here. But if you're just trying to say, hey, hydrochloric acid reacts with metal, produces hydrogen gas, you might use this form when you're writing your chemical equations. And sometimes you'll see that in your books. All right. So we talked in the last section about concentration of ions in solution. That was the last section we talked about. So if we're talking about hydrochloric acid here, I'll use blue here just to mix it up. What we have is hydrochloric or hydrogen chloride gas. When we put it in water, we get hydrogen ions plus chlorine ions. Okay? So this really follows exactly the same rules as what we talked about in the last section. The last section we said, all right, if you have 1 mole of this going in, then how many moles of these ions are you going to get? And we learned from working those last problems that you basically use the equation to figure all this out. Now, in this equation, everything's already balanced. So the way you look at it is, okay, if I put 1 mole of hydrochloric or hydrogen chloride gas into solution, it's going to equally split up, right? So then I should get 1 mole of hydrogen ions and 1 mole of chlorine ions. So it all behaves the same as what we talked about the last section. I'm trying to instill upon you and to make sure that you understand that just because it's an acid doesn't change anything. It's still something you put into water and it breaks down. So last section we talked about ion concentrations. It all applies. So I just want to make sure that you understand that the same rules apply for the calculation of concentration of ions in solution and things like that. If you're given a problem, just like all the problems we worked in the last section where we're calculating what's the concentration of the hydrogen ions in solution, what's the concentration of the chlorine ions in solution, given that you've put so much of this stuff in the water. It's the same exact math, basically. The fact that this is an acid doesn't really change anything. It's still something you put in water, breaks apart, and you have sort of a chemical equation here describing that 1 mole of this yields 1 mole of this and 1 mole of this. All right, so now I want to begin to sort of wrap up the section. We've talked a lot about strong acids, and notice our definition of a strong acid is something that completely ionizes in water, and so because of that it conducts electricity and they're strong electrolytes. So if that's the case for strong acid, what do you think a weak acid's going to be? Well, it's going to be a substance that when you put it in water, it dissociates and it does break down, and so it does produce some hydrogen ions, but maybe it doesn't break down as much. It doesn't dissociate as much as the strong acids over here. And that's exactly the definition. So you will have something you're going to talk about called weak acids. And so only some of the molecules ionize, let me underline this, in solution. The bulk remains as molecules. Most acids are weak. Okay, and because of this, they're weak electrolytes. All right, so this all makes sense with our definition. So some acids, when you put them in water, they'll break down completely. They'll have lots of ions in solution. So you have a high concentration of hydrogen ions and lots of ions floating around, so they'll be great conductors of electricity. So those strong acids will also be strong electrolytes. That's what we talked about before. Here, you'll have some class of substances where only some of the molecules will actually ionize and break down. Most of the molecules that you put in there are going to just remain bound up as molecules. If they don't break down, then they can't give hydrogen ions in solution. So that means they're going to have a weaker concentration of the ions in there. So it's going to be a weaker acid. That's what we call them, weak acids. And because of that, they'll be weak electrolytes because there's fewer ions floating around in the solution. So that's the definition of weak acids. Now what I'd like to do to close the section off is give you a nice listing of some common acids that we call strong and common acids that we're going to call weak acids. So let's do that because you'll probably see a lot of these things over and over again. So common acids, so strong acids. Right, now the list here obviously is going to extend beyond what I'm going to write on the board, but I'd like to give you at least a few. So let me switch colors here. Probably the most common thing you're going to run into is HCl. We've talked about that, and that's hydrochloric acid. Hydrochloric acid, okay? All right, probably the next most common thing is nitric acid. That's HNO3, nitric acid. Okay, after nitric acid, I would say the next most common thing is sulfuric acid. You've probably heard of this. This is battery acid, by the way, H2SO4, sulfuric acid. Let me switch over to red. I like red a little bit better. All right, now we get into some names you may not have heard so much. Here's perchloric acid, and to get that, it's HClO4, perchloric acid. All right, and after that, you have HBr, which is hydrobromic acid. Hydrogen bromine, so that yields hydrobromic acid. And finally, this is the last one I'll name for the strong ones. HI is hydro, and you have iodine, so it's hydroiodic acid. So here we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 strong acids. These are the most common acids. There's definitely other strong acids out there that exist, but in a chemistry class, these are the most common acids that you'll probably see, and they're definitely the most common strong acids you'll see. Notice the way the thing that's in common with all of these. If you just look at the chemical formulas, what do you see in common with every one of these things? Well, here's a hydrogen, here's a hydrogen, 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 hydrogen. They all have hydrogen. And they all have to have hydrogen because in order to make an acid, when you put this in water, these compounds, when you put them in water, they should break down. And because they're all strong acids, all of these are going to completely ionize, completely break down. So all of these hydrogens are going to go into hydrogen ions in solution. And because they break apart completely and flood the solution with ions, they're we call strong electrolytes that conduct electricity. And of course, they're strong acids because of the same reason. So all of these free hydrogen ions floating around solution, when we talk about reactions later, they're going to be able to participate, really strongly in a lot of reactions and very readily. And so that's why we're calling them strong acids. So they give a lot of hydrogen in the solution. So let's go and talk and give you a couple of examples of some weak acids. Now these are acids that are also pretty common, but they're just not quite as strong as the other ones. So these are ones that you'll actually see quite a bit in your chemistry classes as well. So here's one, CH3COOH. I call it CH3COO, right? CH3COO. And this is acetic acid. And by the way, acetic acid you've actually dealt with quite a bit. It's basically vinegar. Vinegar that you buy from the store is acetic acid, diluted with water. So it's not, they try to dilute it and they get it to that perfect concentration. So vinegar is something you can cook with or eat or whatever. So when you buy, it's not pure acetic acid when you buy it in the store. It's diluted with even more water, so it tries to weaken it a little bit so it's not too strong. But compared to something like hydrochloric acid, acetic acid does not break down in water as readily. It doesn't dissociate as readily. But you do notice that there's hydrogens in here that are going to be liberated whenever you put it into water. Okay, another one is carbonic acid, H2CO3. Carbonic acid. And then finally, the only other one I'll probably list is citric acid, which is C6H8O7 citric acid. Okay? And I'll just put in parentheses lemons. And it's not just lemons, it's any citrus fruit. Look at the name of it, it's citric acid. So oranges, things like that. Anything that has that citrus flavor to it is going to contain citric acid. So C6H8O7. Now these are weak acids. This means that all of these compounds, when you put them in water, they will dissociate, they will break down, and so they'll liberate some of their hydrogens into solution, so they'll have some hydrogen concentration that makes it an acid, right? But they don't fully break down. They don't love to break down. So if you actually could zoom in and look at a solution of citric acid, you would see lots of these intact molecules floating around because they didn't break down. And then you'd also see lots of the ions in there that it had also given up and broken down. Compared to something like this, if you looked at a microscope, you wouldn't see any H2SO4 bound together at all. You'd see it all basically broken apart because it loves to break apart. Now, here's the kicker. Even though I labeled all of these up here as the strong acids, and I gave you 3 examples of the weak acids, let me write something in big letters. Most acids are weak. Most acids actually are weak. In other words, most things that yield an acid don't break down fully when you put them in solution. That makes them weak, right? So we've only given 3 because these are the 3 that typically you'll use in a chemistry class. It'll be the most common things you'll see as weak acids. And I've given you a longer list of strong acids. But actually, if you made a complete list of acids, of all the acids known to man, most of them you would find would be in the weak acid category. There's lots of organic compounds, carbon compounds that have hydrogen on the end, that if you put them in water, it'll liberate some of their hydrogen, and so they're classified as acids. But they just don't do it very much. They don't love to liberate their hydrogen. So there's a very long list of things that do that just a little bit, right? But it wouldn't be very instructive to list a long list because you're not going to use them that much. You'll use the acetic acid a lot, the citric acid a lot. Carbonic acid is, sometimes you'll see that in a test or whatever. You do not have to remember this list. But over time, you will just begin to remember typically what's a strong and what's a weak acid just because you'll be using them so much. So that is this section here. I just wanted to give you a good introduction to what is an acid, how do we define what an acid is, and let's try to put pencil to paper and take get a little bit away from the conventional layman's definition of what an acid is and get to what is really important in chemistry. So to boil this whole thing down, An acid is a substance, when you put it in water, it dissociates, breaks down. One of the things it breaks down into has to be hydrogen ions. So we talk about hydrogen ions. So later on when we talk about concentrations of acids, later, it'll be all about the concentration of those hydrogen ions in the solution. Is going to tell you how strong that acid really basically is. All right? And then we talked about the fact that even though we talked about there's two classes of acids. There's the strong acids that break down fully, so they conduct electricity well. And then there's the weak acids that don't break down fully, and so they don't conduct electricity so well. So the strong acids are strong electrolytes, the weak acids are weak electrolytes. All right? And then we talked about, probably the most common acid and how it breaks down. And then I tried to impress upon you that even though, yes, we're talking about hydrogen ions in solution, that actually, when you look at water, what happens is this thing gets bound to water. So it becomes H3O+, which is a hydronium ion. You don't really need to worry about this too much right now. I'm just letting you know, FYI. Some books actually prefer to put this in the equation, and so you see it up front. But I think it's more instructive to say, hey, it breaks down. Let's use this form. Lots of books do it that way. And then later on, just so you know in the back of your head, okay, it's not really these H pluses that are floating around. It's these hydronium ions that are floating around in the water. So because of that, there's various ways you might see that. You might see an acid defined as a hydrogen ion producer. You might see it as a proton producer, because what we talked about with a hydrogen ion is basically a proton. Or you might see it as a hydronium ion producer, as a definition of that guy. And then we made a listing of the strong acids and the weak acids that you're likely to see. So let's close this section off. Make sure you understand everything in here. Follow me on to the next section where we'll talk about bases. We'll do the same kind of lesson dealing with bases. And then at that point, we'll be in good shape to go off and do some problems actually reacting acids and bases together and see what actually happens.